All right, so we're going to be looking at problem number 9 here. This is part 2 of the 2.1 circular motion worksheet. I thought this problem was particularly a little bit difficult, so I wanted to take a look at that. In this problem, we have these two pulleys, one that is smaller and one that is bigger, and they're connected by this belt or chain or rope or something. The connection between those two things is super important, and we're going to talk about why in a second. In the problem, we're given that the 2-inch pulley is rotating at a speed of 3 revolutions per minute, and we want to find what the revolutions per minute of the 8-inch pulley is. Now, there is a hint given with this problem that the linear speed of the pulleys must be the same because they're connected by a belt. That's the key to this problem. Because this belt is touching both pulleys at the same time, and this belt, since it's a kind of a continuous thing, it can't move at different speeds just because it's touching a different pulley, right? So this belt is representing the linear speed of each pulley, and since the belt can only move at one speed as it's going around both of them, the linear speed of these two things have to be equal. So that's going to be kind of the key to what we are doing here. Now, how can we use that, right? So the only thing we really know about these pulleys is the radiuses and how fast they're revolving, which in this case, remember, this is kind of another way that we can represent angular speed in revolutions per minute. Generally, we'll want this in radians per minute, but that's actually a pretty quick conversion, right? If we have 3 revolutions per minute, we just need to multiply this by, let's actually just convert this really quick, 3 revolutions per minute. If we want this into radians per minute, we need to multiply by 2 pi radians divided by 1 revolution. Revolutions are going to cancel out, and now we're in radians. So this is 6 pi radians per minute. Again, radians isn't really a unit, but we'll leave it in there. So that is the angular speed of this smaller pulley. Okay, we already said that their linear speeds are the same. So what I'm going to be doing is making use of this particular equation, V equals RW. And I'm going to make use of it for both of them. We know that the V's, the linear speeds, are the same for each pulley. So I'm going to set the situation up of that the linear speed for one pulley is equal to the linear speed for another pulley. So for my smaller pulley, we have a 2-inch radius times 6 pi over minutes, right? 6 pi radians per minute. That is for my smaller pulley, and that is the linear speed of that smaller pulley. Well, that has to equal the linear speed of my bigger pulley, which has an 8-inch radius, and we do not know its angular speed. That's what we're trying to figure out. But both of these two expressions, right, this expression right here is radius times angular speed. That's the linear speed of my small pulley. Radius times angular speed, that's the linear speed of my bigger pulley. And we know the linear speeds are equal, so these two things would have to be equal. So there we go. This actually becomes pretty easy. We're going to get the W by itself, right? We're just going to be dividing both sides by 8 inches. So I'm going to divide both sides by 8 inches. So divide by 8 inches. Divide by 8 inches. 2 divided by 8, that's going to be 1/4. And then the inches are actually canceling out over here. So we're done with inches. Inches are all gone. So we end up on this side as 1/4 times 6 pi radians per minute is going to equal the angular speed of the larger pulley. Doing this multiplication, right, we can reduce this a little bit. 6 pi over 4 is actually going to reduce to 3 pi over 2. So this is going to be 3 pi over 2 radians per minute. And that is our angular speed of that. Now, the problem asks us for the RPMs, the revolutions per minute of the 8-inch pulley. So that's just going to be a quick unit conversion. So to do that, I want to take my angular speed, radians per minute, and I want to multiply that by 2 pi radians, right? That's going to get rid of the radians unit, so to speak, and that's going to be equivalent to 1 revolution. So now we're going to be in revolutions per minute, and we'll have our final answer. So the pi's nicely cancel out. 2 and 2 multiply together, so we're actually going to get 3/4 when we have that 3/4 revolutions per minute. We could write that as a decimal, but that is the RPM for our larger pulley. Yeah, cool. Oops. All right, let's go ahead and move forward. I'm going to be looking at question number 9. I said 9 and did 10, but you know me, just kind of talking about the wrong numbers. I'm actually going to go back and do the real number 9 now, as intended originally. Okay, so now number 9. That was actually number 10, I apologize. So number 9, we are looking at the speed of the Earth. Now, for this problem, we got to suspend a little disbelief, or at least just recognize that we're making an approximation, because the orbit of the Earth around the sun is not a perfect circle, but it's relatively close to circular, right? Its eccentricity is not too far off of a circle. It's just not a circle. We do know that. So the mean distance of the Earth from the sun. So here's our sun, and we are orbiting around that thing. We'll just have the Earth right here. Obviously, this is not to scale. Sun is way bigger than that in scale, but just in terms of a drawing, that's what we're looking at. And the mean distance, the average distance of that, which is what we're going to call our radius, is, in scientific notation, 9.29 times 10 to the 5th miles. Right? That means we need to actually move that decimal place over 5 spots to actually get the real number. But assuming that the orbit of the Earth is approximately circular, which it sort of is, and that 1 revolution around the sun takes 365 days, we know that's, again, another approximation. It's actually a little bit less than that. That's why we have leap years, or a little more than that. I don't remember which. Find the linear speed of the Earth. This is actually a really simple problem, right? We are just trying to find the linear speed of this thing. How fast is it going around? And we know the radius. And we were given a form of the angular speed, right? We were given that 1 revolution takes 365 days. Miles per hour. We do want the V, the linear speed, in miles per hour. So there is going to require some unit conversion here. Our radius is in miles, but our revolution is actually in days. So we're close here to what we'll need to do. A little bit of unit conversion. So first, this is our angular speed. We'll need to convert that into radians. So 1 revolution every 365 days. Is going to be 2 pi over 1 rev. So now we're dealing with radians per days. Oh, radians per days. This is going to be 2 pi radians per 365 days. Now, again, we don't love this being in days, since we do want our final answer to be in hours. So 365 days, we can do a quick conversion there. I don't need to get too fancy, but there are 24 hours in a day, so we just can multiply that number by 24. So there's 2 pi radians per 8,760 hours. That's a year in hours there. So this is going to be the angular speed that we use. And we have the radius up here. So we can make use of that formula V equals R times omega, radius times angular speed. We're going to multiply those together. And conveniently for us, we've already done all the unit conversion up front. We're going to be doing miles times radians per hour. And remember, radians isn't really a unit in the same sense of these other units, so we will have miles per hour as our final answer. I'm just going to go ahead and multiply those two things together and not write it out. So let's do that. So I'm using the scientific notation 9.29 times 10 to the fifth. So that's, this number. So I'm going to use that times, I had 2 pi per 8,760. Let me just confirm that really quick. Yes. So I multiply my radius, that answer, times the angular speed that we just had to get the speed of the Earth, okay, in miles per hour. So this is 666.33 miles per hour. So that is the speed that we're dealing with. Very fast, very fast. If it wasn't for the gravity of Earth, we'd all be flying around going that fast. All right, so that's number 9, the real number 9, unlike the last one that I asked about. All right, final problem, number 12. Okay, spin balancing a tire. That is a thing that you may not be familiar with, but that's okay. A spin balancer rotates the wheel of a car at 480 revolutions per minute. I'm going to call that RPM. Okay, spinning a wheel at 480 RPM. If the diameter of the wheel is 26 inches, remember that means that our radius would equal 13. What is the road speed being tested by the balancer? Okay, so we want to know if we rotate a tire at 480 revolutions per minute with a radius of 13 inches, what is the equivalent linear speed of that? Okay, that's the first question. So we're going to focus on that one. The second one is asking us if we want to test a linear speed of 80 miles per hour, how fast should they spin it? So what's the RPM in there? All right, so a few things with this problem. We have the radius. 480 RPM is another way for us to express angular speed, though we want that in radians. So let's do that quick conversion. 480 revolutions per minute times 2 pi over 1 revolution. That's going to give us, I apologize there, it's going to give us radians per minute. So we end up with 960 pi radians per minute. That is our angular speed. We will be making use of that, and we will be making use of our radius. There's a bit of an issue here in terms of what we're dealing with, right? Because our radius is in inches, and this is in minutes, and we're going to be expressing our linear speed in miles per hour. So there is going to be some unit conversion that takes place. We could do that up front, but as you can see, if I convert 13 inches into a mile, that's such a small amount of a mile. We're going to be dealing with a pretty messy decimal here. And yeah, I'm just going to go ahead and go straight. I'm going to get my answer in inches per minute, and then we'll convert to miles per hour. So again, I'm going to be making use of this formula. Great formula. Linear speed equals radius times angular speed. So radius is 13 inches times 960 pi radians per minute. Again, radians not really a unit the way that we normally think about units. So we're going to be in inches per minute here. So 13 times 960. This is 12,480 pi inches per minute. Now, again, not the way that we really want our final answer. We want this to be in miles per hour. So we do want to convert that. So we got to do both. We have to convert inches into miles, and we got to convert minutes into hours, right? So we're going to need to do both of those things. So I'm going to give myself some space here to do that. Okay, so I've got 12,480 pi inches per minute. So let's focus on going inches to miles. So inches would go into feet, right? So 1 foot is 12 inches. That's going to get rid of my inches here. And then 1 mile is 5,280 feet. So essentially, we're going to be dividing this by 12 and dividing this by 5280. So that's getting us into miles now. So we've got that taken care of once we do our calculations here. Then we need to go into hours. So currently I have minutes, and I want to go to an hour. Well, I know that there are 60 minutes in 1 hour. So minutes will cancel, and essentially we're going to be multiplying this by 60. So I'm going to do all this calculation in my calculator. I've kept this exact to this point just so that I didn't make any sort of rounding errors. So I'm going to do all this now. I'm going to be multiplying this by 60, and I'm going to be dividing it by these two things. So I have 12,480 pi. I'm dividing by 12 and dividing by 5,280. And I'm going to be multiplying by 60. This one gave me an exact version. I'm going to go into decimals now. So we're dealing with 37.13 miles per hour. 37.13 miles per hour. Sorry, there we go. Pretty fast. Not 80 though, right? 80 was significantly more than that because we wanted to answer the second part of this question, which asks if we want to test 80 miles per hour, how do we get that? So I'm going to make use of that same formula, V equals R omega. We know a lot of these things. In this case, we know the linear speed is going to be 80 miles per hour. So 80 miles per hour. And we do know that the radius is 13 inches. That's not an ideal unit here. So 13 inches in terms of miles, we need to multiply by 1 foot, equivalent to 12 inches, and then 1 mile, equivalent to 5,280 feet. I'm just doing this quick conversion: inches, feet, we end up in miles. So 13 over 12 times 5280. I'm just going to go ahead and write this one out. So this is a fractional version, but that's fine. We're dealing with 1363,360ths of a mile. That's our radius in terms of miles. It's a very, very messy looking fraction, but it will be useful here in a second. So that's our radius, 1363,360ths of a mile. And that's going to be multiplied by the angular speed. And remember, we're looking for the RPM, so we're looking for the angular speed here. To solve this, I need to multiply both sides by the reciprocal of this. So I need to multiply both sides by 63,360 over 13 miles would be in the denominator here to get rid of that, right? And then I need to do that on both sides. So 63,360 over 13 miles. Again, the miles unit is canceling. So we're going to be getting an angular speed on this side because all of this is canceling. I'm going to be getting my angular speed is equal to radians per hour. So let's go ahead and do that. Radians per hour. So 63360 times 80 divided by 13. Doing my calculations here for this number, I'm getting 389,000. Okay, I'm just going to write it down. 389,907.6923. I'm going to write the whole thing, but it's not that important. And that is in radians per 1 hour. Again, our goal here is revolutions per minute. So we need to make a conversion of radians per hour to revolutions per minute. So we'll need to convert radians into revolutions and hours into minutes. So quickly, we know that 1 hour is equivalent to 60 minutes. So that's the easy one. The hours and hours will cancel. And radians, so we know that 2 pi radians is equal to 1 revolution. That gives us in revolutions. So essentially, we're dividing by 60, and we are dividing by 2 pi. So I'm going to take that answer that I just got and divide it by those numbers. So divided by 60 and divided by 2 pi. And there we go. So we would need a revolutions per minute of around 1,034.26 revolutions per minute, RPMs. That one was a little messy. Depending on rounding, you might get an answer that's near this number, but slightly off. But that would be our final answer. To test a linear speed of 80 miles per hour, we would need to rotate the tires at this amount. All right, that's it. Hopefully this was helpful. See you guys in class.